for this year, 2018. So the big word is interferometry. What is interferometry? Is this in your way?
Thank you.
So that's the classic interferometer that is showing us up in, say, an FTIR. And it actually works for gravity waves. There are about 1,000 people on that publication from a couple of years ago, a Nobel Prize in Physics last year. And one of the 1,000 authors is my friend Warren Johnson, also at LSU. And he helped find the site for this interferometer. It's not that I need to know anything about gravity waves, but in this science, I needed to learn about interferometry. And the reason basically started in 2006. This publication, these images showed up in a Physical Review Letters paper in 2006. And there's the classic X-ray image that's been 100 years old. And this is the same sample, take the image, this chicken wing, the same sample imaged at exactly the same time. And now there's a way to see feathers on the chicken wing. And then same sample image at the same time. Now there's a way to see the small details in the bone. And one of my colleagues saw this and photocopied the article and threw it at me. And I looked at it and said, this is just too much math. It looks great, but I don't know how to do this kind of stuff. Well, eventually with my friend, the gravity wave scientist, and his knowledge of interferometry, we pulled it off. Along the way, I had a chance to see the machine that did this. It worked. This experiment worked pretty well. Did you hear that? I am an arrogant, stupid guy, and I go to the guy's lab in Switzerland that took that image, and I said, this thing really worked? Let's try that again. So it worked. This experiment worked pretty well. Okay, what I don't see are millikelvin temperature controls. What I don't see are really elaborate vibration systems because the X-ray wavelength is so small. In fact, it's just standard laser table stuff. This experiment really works. Okay.
How much did you pay for it now?
So, what good is it besides chicken wings? This came out last year. Julie Herson out of the Munich group, Munich, Germany. So here's a mouse that they've induced tumors in. And with the red circles show in the two mice where they can see with the traditional X-ray imaging where the tumors are. They're missing all of these blue ones. And when they dissect the mice, they found two others that they didn't see in the interferometry image, but they're getting really good with that. And I think with a little bit more tuning, they'll even be able to find these tumor sites. So this interferometry, this 2006 invention, the community, and I think there's maybe a couple of hundred of us in the world right now, the community thinks this is going to revolutionize clinical imaging, material science imaging. It's just going to be the way of the future. So I wanted one. In 2006, I wanted one. We had an existing synchrotron, an X-ray source, and we had an existing tomography beamline. I wanted to build on top of that to get one. I wanted to learn how the experiment works, interferometry. It took me a while to learn how to spell it reliably. And it's still a work in progress. I'm still trying to figure this out. 2011, I'll show you the feather 2011 experiments done at the Advanced Photon Source, Argonne National Labs. A lot of math involved. I'm scared of math too. I'll show you my strategy for getting over that problem. A little bit about the funding construction and then what we're doing with it. And then it's got us into a small business type trajectory. And I'll show you what we learned about that, and you might like to do that too. So we have this small synchrotron. Synchrotrons are often 5-10 times larger than this building, but this is the one we have at LSU, and this is one of the pictures of the system under construction. See, it's still a little temporary. We weren't really sure how long to make the system, so we're using these couplers to do that. We're getting that fixed. We're collaborating with a whole lot of people, New York University on some software, Sandia National Labs on some optics, a small company in Belgium, another small company in Germany. One of the things you'll hear about in general chemistry is the de Broglie wavelength, and that's about the last time you ever hear about it. Some physicists, I'm explaining how the 2006 invention came about. Some physicists in mid-1990s in Switzerland and at MIT were just studying helium beams of helium atoms going through a slit and a whole lot of other slits, and they were looking at the interference pattern, the interferometry. And they saw interferometry, and in the speed of this and the size of that, they get these interference patterns. What someone eventually noticed is that the de Broglie wavelength for helium atoms was about the same as the wavelength for X-rays that come out of a synchrotron. Duh. We already know how to make slits that work for atoms, change the material a little bit, change the microfabrication, and you can do the same thing with X-rays and you can get these patterns. And that's the start of the interferometry. It just was these guys in Switzerland said, wow, we've already been microfabricating them for helium, we can just do it for X-rays. And off they went. And so, how does it actually work? Well, here's an intense but nothing special. It's just a very intense source of X-rays, a wiggler, just an arrangement of magnets at a synchrotron and an X-ray source. And so what's coming here are just really strong X-rays, but nothing special. No laser light.
Is it possible to go back to the previous slide? Mm-hmm. You mentioned the de Broglie wavelength. Okay, you have dt over d squared.
Yeah, so this is an equation to say for the Talbot fact that this pattern, these are at Talbot distances. Mm-hmm. And John Talbot was a guy, 1836, he discovered this. He's holding a grating and he notices, oh, in sunlight, there's these colors out here, there's this pattern out here. Mm-hmm. So he didn't really understand it. Lord Rayleigh did the sine cosine derivations for that. But the important part here is that wavelength for these helium atoms is defined by the de Broglie wavelength. Oh, there's one other weird thing I ought to say about this. If the helium flux is really, really low, such that there's only one helium atom going through here, quiz question, does the interferometry still work or not? If there's only one helium atom in the instrument at a time.
You have a wavelength, yeah?
Yeah. Yeah, this is true. Only one helium atom, you still get this intensity pattern. That's one of those things that you want to keep in your mind when you start hearing about quantum entanglement. It's the same issue of quantum cryptography, quantum computing, quantum entanglement. That's also shown up in this experiment.
And because there's no helium dimer, right? That doesn't exist.
Huh?
Helium 2, that doesn't exist.
Right, yeah. So these, to show up, these things are just in an excited state. When they hit here, they emit light. Okay. So, let's see. So this is just an intense, it could be any source. I look at this set of slits. This is a whole bunch of them, like the first one. I look at this as sort of a Young's two-slit thing. So photons come through here, photons come through here. Give them enough time, they do, it's just as I showed with the helium, they interfere with each other. So by the time they get to the sample or to this one, they become phase coherent, which is laser light. They're phase coherent. They can tell whether they've gone through a little bit of refraction or a lot of refraction because they're phase coherent. And they can also tell whether there's scattering going on or absorption. And then this other grating is designed to give a moire pattern because we can't afford to have high resolution detectors. We can't have it's just impractical by a detector that's as pixel sizes as small as these slits. So now that's a very fast pass on the all the details that have to work for this experiment. Here's this calculated phase pattern that says So here's a phase shifting element, nothing happening, phase shifting. So downstream at a Talbot distance, we get this image. And then downstream of here, we get this image. And downstream of here, we get that image. So those are those Talbot distances that were in that equation you pointed out. And here's an SEM of the slits that we're trying. So this is a top view of slits like this. And this is one of the little problems going on with this experiment. So there's these gaps. Those gaps are part of the, let's develop something to hold up the microfabricated device while we're making it to keep it from falling apart. Ideally, we would never want these things. They cause problems. And they just illustrate, even though we're microfabricating this stuff, it's still at the state of the art for the microfabricators. And then when
you don't mind, stop it.
Please.
What's so important about a tablet distant?
It defines how big this instrument's going to be. If we do X-rays of this wavelength, and we had our microfabricators give us 4.8 micron period gratings, then we know it's going to have to be this big.
Okay.
And we would like to make it smaller, but we can't get the microfabrication any smaller. Now at the detector, I'm going to show you some more pictures of this, but at the detector, a given pixel, a given detector, is seeing a sinusoidal signal strength because it's sinusoidal because this one grating is being shifted. This could have a 4.8 micron period. It's being shifted by distances of a fraction of 4.8 microns. And so over here at this pixel, by the time we go through the Moiré pattern, depending on where we move this detector, we get a lot of counts, a medium number of counts, a lot of counts, or very few counts. That's the interference pattern showing up. That's without the sample. We put the sample in, we see whether there's been refraction or scattering or absorption. So I heard about this experiment. I called up some people that I knew at Advanced Photon Source. They said, we got a group that wants to put this together and try it out. We'll put the two of you together. We need a particular sample that'll be bizarre for X-rays. I talked to my biologist. I said, I need a bizarre sample for X-rays. She says, how about a feather? No one ever does X-rays on a feather. So we did X-rays on a feather. That was a real cool idea. And the optics of it are such that this field of view is about 1 millimeter by 1 millimeter. That's a very thin barb of a feather. And this is all of those images that make up the sinusoid. So as you look through this, you can sort of see it's bright, it's dim, it's bright, it's dim. It's got some little spots through there. Those are those defects. So there's a difference between with no sample and then with the sample in there. And we're trying to calculate the three different images. And we calculated the transmission image, this one, whether or not the feather's absorbing any X-rays. The diffraction image, whether or not the feather is bending any X-rays. And you see that the edges really show up. And then the scattering image, where the X-rays go in and just sort of scatter off small structure, and the center part is really a scatter. So that was our first attempt, and we thought, wow, this is pretty cool. We kind of know how this experiment works. But to make